it was basically I wanted to show you what are the different examples are there in your stick diagrams and how you can create the stick diagram for the any given circuit. So for that I have used that document. Okay, so today we will go for these design rules and layout once again, and in details we will be going through. Okay, so as I told you in the last classes, so the design rules will enable us to design the circuits with a miniature precision values with a advanced improvements in the performances. We can do it. Okay, so because basically we will be using one of the important design rules in the case of VLSI technology, that rules we are going to call it as a lambda based design rules. So this lambda based design rules will mainly works on one of the simple parameter or one of the single parameter that is called as a lambda. Okay, so therefore the name of the design rules, why it has been called as lambda based design rules. And whenever you want to create or whenever you want to specify any one of the parameters in the case of VLSI design, then you need to mention the minimum size, or we call it as a miniature size of the design. So the miniature size of the design in the case of lambda based design rules, we are going to call it as a 2 lambda. Okay, and generally we will be representing these design rules in order to fabrication of your VLSI technology. So still now whatever we have done is, so we have, when they give you any boolean expression, for the boolean expressions we have drawn the circuit. So either it may be a CMOS technology or it may be a MOS technology. So for that CMOS technology we have drawn the stick diagram, and after drawing the stick diagram we will be writing the layout. So when you are writing the layout, so there you need to be very careful. So what is the length and width you are going to consider, so that the whatever the length you are going to consider, it will not exceed, or the excess length you are not going to use in the design of the mask layout. And also the distance between one layering to another layering, it has to be precise, and it has to be short, and it has to be appropriate, it has to be optimum. Okay, so in order to have these features, so we are going for lambda based design rules. So as I told you in the last class, these lambda based design rules will be facilitated or will be used by using two important component, that is nothing but length and width. Okay, or it may be width and length. Okay, so you can see here, so one of the simple transistor what we have considered is nothing but NMOS transistor we have considered. So in the case of this NMOS transistor, you can see the substrate whatever we have used, that we have used the substrate is equal to p-type material, that is a silicon material we have taken, and for this silicon material on top of that we have deposited or we have sandwiched two channel material, that is nothing but N plus material. One will act like a source and one more will act like a drain. So on between them we have created one polysilicon. So with the use of this polysilicon, with the apply of some voltage across this polysilicon, so we can able to establish a channel between source to drain, so that the channels, or so that the carriers will move from source to drain. Okay, so that is the basic fundamental what we are creating the transistors. So for these transistors we have already know how to draw the stick diagram. So since in NMOS transistor the channel it has been created from the N plus diffusion, so therefore we have created a N plus diffusion with a green color. So you can see we are going to represent the width of the channel. You can see that we are going to represent the width of the channel in the form of W. We are going to represent the width of the channel in the form of W. So this width corresponds to the width of your N plus diffusion. Just wait a minute. So we are going to represent the width of the transistor as a W. Similarly, the length, that is a polysilicon whatever we are going to deposit, the width of that polysilicon we are going to represent with terms of length L. Okay, so polysilicon is L and the length whatever we are going to call, that is a channel. So the channel length we are going to represent in terms of W. So when I say or when I write any design rules, then I need to specify this W and L. So that is W cross L we will be specifying. And in the case of lambda based design rules, this generally will be miniature size that we are going to consider 2 lambda. That is nothing but 2 lambda cross 2 lambda. So 2 lambda is nothing but the width of the channel, that is for the end diffusion, and 2 lambda, that is for the width of the, that is a polysilicon what you are going to draw. Okay, so this is how you can able to identify the length and width in the case of transistors. Okay, so I request all the students, you please make a note of this diagram and we will go for the next. Okay, next. So you can see how exactly the mask layout will look like. Okay, so how we are connecting the metal, and from metal 1 it has been connected to metal 2, and from this metal 1 it has been connected to a polysilicon. And we know that polysilicon directly cannot be deposited on top of the substrate. So before that, what we will be doing is we will be placing a thin oxide. So thin oxide is nothing but silicon dioxide we will be placing on top of the substrate. So for the polysilicon, we will need to connect a metal. So the metal one what we have connected is metal 1, and there is a connection from metal 1 to metal 2 via through the use of wire connections. Okay, so this is how we can able to establish a connections in the case of lambda based design rules. So this is one of the simple examples what we are going to see it. Okay, next. Okay, so now see, if you remember when we are doing with the fabrication process, three important fabrication process we have studied. One is nothing but NMOS fabrication MOS process, and one is CMOS fabrication process, and one more we have studied, that is nothing but twin tub fabrication process. So this is a mechanism how we are going to do the fabrication. Just wait a minute, someone is joining. This is a mechanism, that is a fabrication process what we are going to use in the case of fabrication, that is a twin tub fabrication process. So in this twin tub fabrication process, twin tub fabrication process, so we are going to incorporate both NWEL, that is NMOS transistor, and PMOS transistor in a single substrate. So therefore you can see we have taken a substrate. On top of the substrate we have created two tubs, that is nothing but one is N tub, that is with a N plus material, and one more is a P tub, that is nothing but P plus material. So for the N tub we need to deposit, that is nothing but we need to sandwich two channels, that is nothing but P plus material. And similarly for the P tub we need to create, this is nothing but NMOS transistor. So for the NMOS transistor we need to create a two channel, that is nothing but N plus and N plus. So now you can see how there is a connection between one source to drain. So since it is an inverter diagram, okay, so you can see how the drain and connected, and how we can establish a connection from metal 1 to and metal 2, so that it can be connected to some other system. Okay, so this is one of the symbol rule what we are going to use in the case of fabrication of twin tub process. Okay, so this is also we have studied in the case of module number 1. So there we were mainly concentrating on how we can establish the NMOS transistor and PMOS transistor with the use of substrate. Now we are going one step ahead. So what is one step ahead is, okay, I know what is the process of fabrication for NMOS transistor and PMOS transistor simultaneously. So after doing the fabrication process, how I can establish a connection with the outside world. So that we are going to deal in this module. Okay, so this is one of the simple process what we are going to use in the case of twin tub fabrication process for the design rules in the connection between one transistor to another transistor. Okay, so now so yesterday also I told you regarding the lambda based design rules. So these are the lambda based design rules what we are going to use in the case of NMOS transistor and the PMOS transistor. So we can see, so basically what we are going to use it when you want to create any NMOS transistor and a PMOS transistor is, so we will be having three important mechanisms, or we will be having three important elements. So what are those three important elements we will be having is, one, we are going to use a polysilicon, and one more we are going to use the diffusion, that is a n plus diffusion, or it may be a p plus diffusion. And one more what we are going to use is we are going to use the metals. Okay, so we are going to use the metal in order to do the interconnection from one layer to another layer. Okay, so if you are using these elements means, then what is the length and width of these elements you need to take care, or you need to understand. Okay, so the lambda based design rules for the case of that is for the polysilicon, it has been given in a red color. So you can see the polysilicon, the width is 2 lambda. Okay, and the distance between one polysilicon to another polysilicon, you need to ensure the distance between from one polysilicon to another polysilicon should be 2 lambda. Okay, so this is the rule what we are going to follow when we create an inverters, or when we create an transistor, or when we create some a simplification of your boolean expression. When you are going to do the mask layout of any circuit or any boolean expression, so these are the lambda based design rules what you are going to see it. Okay, so this is which is related to polysilicon. Next, similarly we go for the diffusion. Okay, so the diffusion what we have taken it over here is, so that is nothing but n plus diffusion, because it is in green color. Okay, so we know that green color will be used for n plus diffusion. So you can see the width of the n plus diffusion, we have taken it as 3 lambda, and the distance between one diffusion to another diffusion. So if you are using two diffusions simultaneously in one circuit means, then the distance between from one diffusion to another diffusion, it has to be minimum of 3 lambda. So this is the rules which has been set in the case of lambda based design rules. So the next one is in case of metal. So okay, the next element is we are going to use the metal. So in the case of metal, you can see there are different types of metals we will be using. Okay, for the interconnection of two different layers in the mask layout. So it may be metal 1, it may be metal 2. Okay, and we know that the differentiation from metal 1 to metal 2 we can do with the use of lines. Okay, so depending upon the thick lines or depending upon the thin lines, we can able to differentiate the metals, or also with the different colors also we can able to differentiate. So you can see the metal, the distance means the width of the metal one we have taken it as 3 lambda, whereas the width of the metal 2 we have taken it as a 4 lambda. Okay, and the distance between one metal to another metal, that is metal 1 to metal 1, it has to be 3 lambda, and similarly the distance between metal 2 to metal 2, it has to be 4 lambda. So you can see on the below of this diffusion they have given you the transistor, that is a fabrication process. So how we can able to establish the mask layout with the use of, okay, so these are the lambda based design rules what we will be using for the each elements in the transistor. Okay, so now you can see here the lambda based design rules for the NMOS transistor and a PMOS transistor. See how we are placing them. Okay, so what we have taken is, first we have taken the polysilicon horizontally, and for that polysilicon we have incorporated, that is vertical, we have placed the N plus diffusion. Okay, and you can see the width, that is the channel length, we have taken it as 3 lambda, and the width of the polysilicon we have taken it as 2 lambda. Okay, and you can see the edge, wherever you have edge, see here the minimum distance is 2 lambda we have taken, and the distance from the where your polysilicon you are placing to the end of your N plus diffusion, we have taken it as 3 lambda. Okay, so this is an NMOS transistor. So here some of the mistakes generally what we are going to do in the case of when we are designing the mask layout is, so you can see in the right side it has been given catastrophic error. See here the transistor, that is a polysilicon, whatever you are depositing, so it has to prolong after the channel also, but here you can see before the channel is ending, the polysilicon deposition we are making it is stop. Okay, so if you write like this means, then you are not going to get the exact characteristics of the transistors. So therefore you need to avoid these catastrophic errors when making a lambda, that is mask layouts. and you can see at the bottom unrelated polysilicon and diffusion. So if you are, when you are going to do the diffusion, so if you are do not crossing these two layers, or if you are if you are maintaining a minimum width of 1 lambda, means again it will be will leads to a catastrophic error. Okay, and you can see the right side of the second diagram, that is a fourth diagram, thinner diffusion, but still it is working. So even though they are, you are going to place them, but still it will work according to your the desired characteristics. Okay, shall we go for the next one?
Yes, sir.
Okay. So now this is which is related to contact cuts. Okay. So we will be using the contact cuts wherever you will be using the contact cuts is. So whenever you are making the cross connection from one coloring to another coloring, then you should make use of the contact cuts, especially when you want to connect the source of that is a drain of PMOS transistor to drain of NMOS transistor, means then directly you cannot have a connection from drain of PMOS transistor to drain of NMOS transistor. So there what you are supposed to do is you need to use the metal. So when you use the metal, so the at the end point you need to have a contact from metal to your drain of your PMOS transistor and the drain of your NMOS transistors. So in such a cases, we will be using the contact cuts. So when you're using these contact cuts, how you're supposed to use those contact cuts, it has been discussed or it has been shown in this diagram. So you can see the polysilicon contact, that is nothing but from metal to metal one, that is nothing but 3 lambda has to be there, the spacing, the length and width, it has to be 3 lambda. So you can see how the contact cut has been placed on top of the polysilicon. Okay, so similarly, if you want to have a connection for the P plus diffusion or N plus diffusion, so you can see the contact cuts. So what is the length and width you are supposed to consider? That is nothing but they have given it as 4 lambda and 4 lambda. So these are the rules what you need to follow when you are writing the mask layouts. Okay, and you can see the distance between one contact cuts, that is nothing but from the diffusion contact cuts to polysilicon contact cuts, it has to be minimum of 2 lambda. So these are the rules you need to follow when you are writing the mask layout for CMOS technology or also for the BiCMOS technology. So you please make a note of these contact cut spacings. Now you can see this is one more example. See, we will be using one more important cuts, that is a contact cuts. We are going to call it as a vias. Okay. So when you want to make a connection from one metal to another metal, or when you want to make the connection between two metals, then we will not call it as a contacts. Instead of that, we will be calling it as a vias. Okay. So if you want to make a two metals to be connected, if you want to make a two metals to be connected of different metals, or it may be same metals in some situations or in some special cases, then we are going to use one of the special contact cuts, and these special contact cuts we are going to call it as a vias. Okay. So when you want to use the vias, there also you need to make use of the design rules. So what are the design rules we going to follow is that they have given it in this diagram. So you can see the via contact cuts, the length and width they have specified, that is nothing but 2 lambda, and the contact cuts, that is a via what you are going to place. So from the via where you are going to place to the end of the contact, it has to be minimum of distance of 1 lambda. And the difference between from one contact cut of wire to another contact cut, the distance should be minimum of 4 lambda. Okay. So you can see polysilicon how we have connected via over the normal contact cut and also over the via contact cuts. See this via it is not different. This is the inverter what we have taken, that is a CMOS inverter what we have taken, and how wherever there is a connection is there, and the corresponding stick diagram and corresponding the that is a mask layout how we have written. So you can see it over here. Okay, so for n plus that is a plus VDD, we have taken one metal, that is a metal one, and where we have one transistor, that is a PMOS transistor on top of that, and a NMOS transistor at the bottom case. So therefore we can say it is a CMOS technology. Okay, and since you can see the PMOS diffusion, it has to be connected to NMOS diffusion here over here. So directly you cannot make over here, so therefore you are using the contact cuts over here, and these contact cuts are connected to metal. So these contact cuts are connected to metal, and you can see this polysilicon and this polysilicon both are interconnected. And when you and I we also told you that, and you also aware that when two same colors or when two same elements, if they are combined or if they are made interconnection, means there is no need to have a need to have a placement of contacts on top of that. Okay, so you can see, so the metal one plus VDD and the bottom one metal 2, that is a metal one, that is for the ground. Okay, we are here placing, and we are placing, that is a P plus transistor, that is a PMOS transistor on top, and NMOS transistor on the bottom, and this is a polysilicon contacts, that is nothing but connecting gate of PMOS to gate of NMOS transistor, and these contact cuts are over here, that is a P plus diffusion and N plus diffusion is there, no? So those are connected to metal, no? So that is this connection, and from here you are taking the output. Okay, so this is the mask layout of this. So of course we have not given the coloring, but here we are making sure that where and all you, this is also correct the stick diagram, and this is also correct the stick diagram for this CMOS inverters. So you just make a note of this, and we will go to the next section now. See, both the stick diagrams same only, but you can see how different they have written. Okay, so this is a conventional method of writing the stick diagram, but you can see the same stick diagram they have represented in a different manner. And one thing you need to make sure that whatever the stick diagram you are going to write it, no, so it should occupy minimum spaces, or it should occupy the minimum area. So in that vision you need to write down your stick diagram and a mask layout for any boolean expression simplification. So that is nothing but lambda based design rules for the metals. Okay, so the metals whatever we have discussed, so the same thing we are discussing over here is, so you can see we have taken metal 1 and metal 2 with different spacing. So you can see the metal 1 we have taken with same one, that is nothing but 4 lambda, but you can see the metal 1 and metal 2 they are differ in the lines how we are representing. You can see metal 1 is also blue color and metal 2 is also blue color one only, but the slope you can see how they are writing. So for the metal 1 we have written a positive slope, and the metal 2 we have written a negative slope, and the width what we are specifying in this case for the metal 1 and metal 2, it will be 4 lambda, and the distance between from one metal to another metal, it has to be 4 lambda also. So similarly for the diffusion, that is a n plus diffusion or a p plus diffusion, so in this case we have taken it as 4 lambda and 4 lambda, and for the polysilicon we have taken the width as 2 lambda, and the distance between from one polysilicon to another polysilicon we have taken it as 3 lambda. And at the bottom case you can see we have a metal 1 to diffusion contact 1, that is nothing but 1 lambda we have taken, and for metal 1 to polysilicon contact we have taken, that is the contact cut we have placed in the form of 2 lambda parameter. Okay, so similarly for the metal 1 and metal 2 connections we have used the vias. So you can see the distance between the two vias we have maintained as 3 lambda. Okay, and this is how the connection will look like. That is nothing but this is a CMOS inverter what we have used. For this CMOS inverters you can see how the mask layout is looking, and the distance between from one transistor to another transistor, so you can see it is 6 lambda and from 6 lambda. So totally it is 12 lambda is there, that is from drain to drain. So drain of NMOS transistor to drain of PMOS transistor, the distance between them is 12 lambda. And you can see the polysilicon we have deposited, and the polysilicon whatever we have deposited, so it has extended. So how much extended? It has extended a minimum of 2 lambda over here. You can see here, this is a detailed analysis of how they have written the contact cuts, what is the width of these contact cuts, everything they have given it in this diagram. So you can see here the first one, whatever the anvil we have created. Okay, so for this anvil, so we have a VDD. So the distance between VDD to the anvil, so it has to be 4 lambda. You can see it has to be 4 lambda. And since I told you we have used the metal one which has to be of 4 lambda width, so you can see the 4 lambda is there. And the distance between via, that is the metal to where we are placing the N plus diffusion, where we are placing a N plus diffusion, because it is a PMOS transistor, right? So where we have placing a N plus diffusion, so we have taken it as 4 lambda. And the distance of the that is the diffusion, what we have taken, the width of the diffusion what we have taken, it is 4 lambda. And the contact cuts what we have created, that is nothing but from where we are placing the metal, from that metal to the end well, it is given as 6 lambda. So means that is the distance what you need to maintain from end well to your metal what you are placing. Okay, and similarly you can see here, so from VDD to wherever you are placing this N diffusion, right? So it has to be 6 lambda only. And the width from here wherever you are placing this N diffusion, so from ending point of the N diffusion to your N well, minimum it has to be 6 lambda. And also from N diffusion at the bottom side also it has to be 6 lambda only. And the polysilicon what we have taken, it is 2 lambda width. And the distance between, that is a polysilicon with a metal one, we have taken it as 1 lambda. We have taken it as 1 lambda. At the bottom side you can see here the minimum width we have maintained after the contact cuts has been created, that is nothing but ground. So we are maintaining it as 2 lambda. And for the contact cuts we have taken it as 4 lambda. And the distance between from one contact cut to another contact cut, so we have maintained it as 4 lambda. Among this 4 lambda, so you can able to see here, among this 4 lambda, 2 lambda is been occupied by the polysilicon, 1 lambda over here and 1 lambda over here. So totally it is 4 lambda. And followed by we have a metal, so this metal will be constituted by 4 lambda. And the ground extra prolongation we have done, so that extra prolongation how much you have to do it, minimum of 2 lambda you are supposed to do it. So when you add the entire thing, so what will be getting, 2 plus 4 6, 6 plus 4 10, 10 plus 4 14, plus 2 16. So then the length, that is a length what you are going to draw, that is it may be VDD or VSS or it may be ground. So you need to take it as 16 lambda, so that you can place both your N transistor and P transistor according to the design rules which has been specified by the lambda based design rules.